take your readings again. Dial it in, slow. And I can't stress this enough, if you have a TXV, same things when you're charging. It is slow reacting. Put in a half pound. Give it a little bit. Take your reading. You start just slamming in 2 pounds, you're gonna flood that evaporator, and then you're gonna be overcharged. Now you're pulling charge. They're looking out the window like, what is he doing? Like, I'm just saying, be patient with the TXV. So here is your superheat spring. This is pushing up on this metering pin, which is an opposing force to your diaphragm. Right here is your pin carrier. This is what is holding your pin. And right here is your inlet strainer. You probably won't see that very often. Again, bigger TXVs, a more commercial environment, but this is kind of like a filter dryer. It is there to protect your TXV. You can change that. Pump your system down, seal your refrigerant down into your condenser. This cap comes off, this comes out, put a new one in, pull a vacuum, release your refrigerant, and there you go. So it's pretty cool. You definitely want to protect your TXV, but you're not going to see that again very much in residential. This is your valve port. This is where it is metering. So now you're taking high pressure. The way I describe it is like picture a flowing river. It's flowing really fast, a lot of pressure. Now it hits a dam. And then you open up just a little floodgate. That's kind of what we're doing here. So we got high pressure on one side, and then it's trickling out on the other, which allows us to change state. So right here is where it's metering. And as you can see, I'll point this out several times, it's got like an angle here. So if it was to go all the way up, that would seat there and seal it off completely. As it goes down, it meters, allows the refrigerant to go through on both sides. Here is your diaphragm. So this right here, the one I'm going to show you, I was really upset when I pulled it out of the unit the other day. A lot of them you can unscrew. That is completely separate from this. This just threads in on a lot of them. The smaller units, it does not. It's just all one piece. But the reason I'm bringing that up is this has refrigerant in it, and it's not this refrigerant. It has its own charge in here, all the way down here, and there's charge in here. You have a diaphragm. It's just a thin piece of metal. And as you build that pressure, it flexes. And it will flex to push against your pin, and it will flex to push against your evaporator pressure here. Let's see, this whole thing right here is your power element. We're going to go over that here in a little bit. And here is your sensing bulb. So again, refrigerant. This is strapped to your suction line. It reacts to the pressure, builds up pressure in here, builds up pressure, pushes down against that, and that's how more or less refrigerant comes through here. So see how you literally pull it off and it looks just like this. You have your buffer plate, which protects it from the pin damaging the diaphragm. This is the top is a stainless steel material, obviously to protect from corrosion. Your diaphragm, again, thin piece of metal, and your thermal ballast. It's kind of a cheesy old school picture, but I loved the picture because it kind of shows what's going on here. You see, it's probably cool, so you don't have a lot of pressure built up. So as you see, here's your diaphragm. Your opposing spring is fully up, and your opposing pressure is going to lift up, which is going to close this off. Here's your evaporator. Now as you see, you've got some temperature here, which is going to build up your pressure in your bulb, travel down. This is over exaggerated. It does not flex like that. It's just very subtle. You'll never even see it. But now you can see it's pushing down on the spring. It's opposing the pressure from your equalizing tube, and that is allowing more flow to go through. So that would be like if you have a hot house and have like a high load. So we have a basic refrigeration class. I highly recommend you guys take it. I'm just going to briefly go over it just to show the importance of why I want a liquid going into my TXV. So you have your compressor, the heart of the system. Here it's taking its low pressure gas, vapor, and turning it into a high pressure, high temperature vapor. Now it's going into your discharge line. In commercial, if you ever accidentally touch that, you're going to know it. It is really hot. Here we are. Here's your condenser. Here's your fins. Here's your lines. Just picture a fan right here. We are actually cooling, even though this is high temp, on a 90-degree day, we are still cooling this refrigerant. That's why they call it condensing. We are taking it from a hot vapor, and then eventually we will be subcooling it down here. So we are dispersing our heat outside. You should get about a 30-degree difference from here blowing out the top, if everything is appropriate. Your coils are clean, things like that. That would be the first thing I'd ever check. If you have 40 degrees coming out, wash your coil. At least start there. Then start ruling out other things like TXV adjustments and things like that. So now, this is about where our superheat starts. That is when the refrigerant is now a full liquid. That is why with a TXV we take subcooling, because we want to assure that this liquid is all liquid going into here. Because when it is designed to flash and change state here, if it starts flashing here early, it's going to mess up the whole design of the whole thing, and you are going to have issues. So here's your liquid line, filter dryer. You do see those get clogged up. If you want to check if you have a clogged filter dryer, or if you want to see if you're going to blame your TXV that's maybe shut, take a temperature difference across. I usually use a clamp. That's my favorite. I know some guys will just take a thermometer, tape it on. It's okay, but buy a clamp. Just clamp it on, goes right to your meter, tells you your temperature. We want to keep that under 3 to 4 degrees. If it's more than that, that filter dryer is clogged. That's a pain in the ass, because now you're going to have to recover the refrigerant. You can't pump. Well, actually, you can pump it down, cut that out, put a new one in, pull your vacuum, and there you go. So again, full liquid into your TXV, which is your metering device. Now, like I already showed you, it comes out from all liquid to part liquid, part gas. We are already starting the process. So now, as it travels through the evaporator, it is starting to evaporate. A little by little, it's becoming 50%. Now it's half-half, half liquid, half gas. By the time we get here, we want it full vapor. But we don't want it too late because we want to protect our compressor. We don't want it too early because we want to utilize all of this evaporator capacity. And then obviously here's where your bulb is and your equalizer. So then it's taking your temperature here, and that tells it where to open and close. So as you can see, high pressure liquid, that's a better picture right here. You see how it's angled. This little discoloration mixture here, that is where it's flashing. I don't know if you've ever looked through a sight glass and you see the flashing, it's pretty cool. Or if you look online and you see they've built a system that's like tubes, and you can watch it just change from a liquid. It's pretty neat. Here's your opposing spring, and then you have your pressure from your evaporator and obviously your diaphragm. So then it is metering this in. So here, let's just say, if that's what it's metering, just a little tiny bit, and that causes it to change state, that causes it to flash, that's your little floodgate. You don't see it often anymore, but you're going to still see it, which is an orifice. Does anybody know what an orifice is? I mean, all it is just a tiny little hole. So now, it's just a tiny little hole. Same concept, it's still gonna slam into that and come out a low pressure vapor. We just don't have the kind of control to keep this capacity. It still should, if your charge is right, your airflow is right, your condenser's clean, if everything's perfect, it still should maintain your superheat like it's designed to do. But it won't adapt to the load as well as a TXV. That is why a TXV is that much better. It's just that much more efficient. So as you can see, here's where it meters, here's where it flashes. But now we're taking a high pressure, 100-degree liquid. As we slow it down, we lower the pressure. Well, pressure is temperature. So now it just dropped 60 degrees. Now we have a low pressure liquid and vapor. We're going to talk a little bit more about balancing. Can't stress this enough. Reads the temperature. Here's where your superheat starts. Puts your pressure. This is your opening pressure. That is P1. Evaporator pressure. That is your P2. And your superheat spring is P3. P2 plus P3 equals P1. And what they're saying there is, again, this is slow reacting. Once your house is 70 degrees, this is probably just going to stay right where it's at. Your house isn't just going to change 30 degrees in minutes. I mean, you could open all the windows and, like I said, people start showing up. But again, it's slow reacting. It's going to start like heating up for the people in your house. As airflow is circulating, now your superheat is here. Well, the temperature adds up. It's going to allow more refrigerant to go through. So it's very slow reacting. That's why they call it's balanced. These are two different types of TXVs, conventional and a balanced port. You will not see much of this anymore. This is more old school. You have a 2-pin, or the pin here, you have the 2 arms here. The only reason they're kind of moving away from this one is your liquid pressure can cause what's called an opposing force, of like a fourth factor on that equation. I'm not talking about it too much because you don't really see this much anymore, but it can affect this pin, which can cause a little bit of disruption. They have now created what's called a balanced ported TXV. So right here, as your pressure comes in, this is a single pin, but they created it so when the pressure comes in, it's pushing up, but it's also pushing down. It's just the way they built the valve. Now it just balanced that out and took that liquid affecting that out of the equation. Here's your packing. It's usually like neoprene, something like that. When you were brazing a TXV, this is kind of, we're trying to protect your head, but we are also trying to protect that material. You don't want to overheat that material. Obviously, if you do and it starts cracking, now the whole design of the TXV goes out the door because now it's going to start metering in a lot more refrigerant. I just use a towel. Dip it in some water. If you have a towel in your bag and you're on a roof, you can just dip it in water. Just wrap your towel thoroughly around both of these and go ahead and do your brazing. But that is what we're trying to protect on a TXV. If this starts turning red hot and you feel like you're overheating, just take a break, come back to it, start over, and then finish your braze. Please protect, you do not, I never burned one up, thank God, but they're such a pain in the ass that I don't think you want to go turn one in warranty and they're looking at it and it looks like you just cooked it. I don't think it's going to be covered. All right, now we're going to talk about internal equalizing port and external. You're probably not going to see this unless you do like gas stations. You know those like little coolers where like it's like a little fridge where you're going up. It's like half-ton, one-ton units, but you're equalizing opposing pressure. It just comes from the outlet here, so it just kind of comes in and goes right here. Really small. It's built internally. I've never even seen one because I obviously I only go to people's houses and I was doing commercials, so we didn't do refrigeration and things like that. You're going to see more of this style. This is coming from your equalizing tube, which it's just downstream from where we mount our bulbs. But that is your opposing pressure from your evaporator. This is a little bit different. This is called a bleed port. So it actually is bypassing what we have going on here. It does not matter what TXV is doing. You are getting, depending on the size of the TXV, they adjust for this per size, per manufacturer. You don't need to know that, just order it per model and serial. But the main reason for this is to protect your compressor. If you have a single phase compressor with low starting torque, it's kind of like they always tell you, don't start a compressor when you have a high pressure load, when it's not balanced out. This is what helps give that time to equalize before we start a compressor. Like when you program a thermostat, you have that 5-minute delay. Well, that's what that 5-minute delay is. Heating, you can just turn on and it'll come on. Cooling, you get that blinking light that when you're on a service call, it feels like an eternity. But that is why we do it. We don't want to start a compressor with uneven pressures. You want them to be equalized. I know they go over this balance a lot, but here's your P1, your opposing force, this is your opening, this is your closing forces. P2 plus P2 equals P1.
So there's no way for us to calculate that. That's something that.
No, these are engineers that are way smarter than me.
Okay.
It's all designed, again, as long as you're ordering the right TXV, we're going to go over that later in the troubleshooting. If you have the right TXV, if you're a thorough technician and you're making sure your filter's good, your airflow's good, because if you suspect something's going on, I would start with all your basics: filter, outside coil, inside coil, rule everything else out, check your subcooling. We're going to go over all that in the more fun part of this. But yeah, it's all balanced out from the factory. So FC equals Fs plus Fe. All right, so we're going to talk about sensible and latent heat. So sensible heat, something you read with a thermometer. So you have 1 pound of water at 72 degrees. You add 140 BTU of sensible heat. Now you have 1 pound of water at 212 degrees. Latent heat is the energy applied that is to change the state without changing your temperature. So that's when we're flashing off and we're converting it completely, or when you're boiling. So now you're going 1 pound of water at 212, 970 BTU of latent heat. It's still 212, but it went from water to steam. 1 pound of steam, 8 BTU of sensible heat, you got 220. So let me ask you, I brought this up for a reason. What would subcooling and superheat be? Would that be latent heat or would that be sensible heat? Latent. Anybody else? It's sensible heat. And the reason I say that, sensible is when you're adding heat, like subcooling. Once it reaches the end of that evaporator and it turns fully to a gas, it's already changed state. That's where the starting point of reading superheat. From that point all the way till it reaches the compressor, that is building up superheat. Because we are adding heat, and it's actually a measurable heat. Same thing with subcooling. The moment it gets to the bottom of that condenser and it is fully turned to liquid now, it starts building up its heat. That's how we know that you are fully charged and we are, or with the TXV, and we are fully liquid up to that TXV.
So sensible heat is changing the temperature without changing the state, and then latent heat is changing the state but not changing the temperature.
Correct. I mean, the only reason I brought that up is just so you can understand, the differences that were, the amount of heat it takes to change the state, but really, the sensible heat measured with a thermostat or a thermometer is a lot more important to us. Measuring superheat and subcooling is huge in troubleshooting. So as you can see, here we are our saturation temperature, because when I mean saturation, part liquid, part gas, it's saturated. Right here, now it is not saturated, it is a full gas. So if you want to know your superheat, you're going to take your clamp, you're going to take your action temp minus your saturation temperature. We're going to go over that in a little bit too. And you have 10 degrees of superheat. Here, same thing. In refrigeration maybe, it's still the same thing. Negative 30 minus negative 40 is 10 degrees of superheat. So here it kind of actually shows you. Right here, you're taking your suction pressure. You have 58. Obviously, this is probably R22. You were going to take it, you're going to convert it on your chart, and it shoots out this number for you. Does anybody use this chart, or do you guys use apps or?
On the gauges.
On the gauges. I always liked using, there's an app, and if you want to see me after class, I'll show you the app I used to use. You can actually take your wet bulb, your dry bulb, and these two temperatures, and it will just calculate and tell you remove or add. And it was really cool. And it does subcooling, it does airflow. It was a really nice chart, nice app to have. So anyways, the chart, which was created by somebody a lot smarter than me, decided that this converts to 33 degrees of saturation temperature. And then we take our actual temperature. Again, I take it with a clamp. I think it's the most accurate. Don't use a laser. I'm just saying there's a time and place for that. Now we just subtract it, and we have 7 degrees of superheat. So in AC, we kind of want to see 10 to 12 degrees superheat. Read the instructions. It's a different world, especially now. I mean, back before, that was kind of just the Bible. That was it. Now, the instructions, they might want other superheats. They easily. So just read manufacturer's recommended superheat. But if you don't see anything, you don't have the book, you're pretty safe with 10 to 12. So that's anything above a 30-degree evaporator. Your walk-in coolers, I don't know if you guys do that, but 5 to 10 degrees, that's anything from a 0 to a 30-degree evap. And your low temperatures, 2 to 5, that's more like your freezer. But I can't stress enough, follow the manufacturer, please. It's more on subcooling, you're going to see that than superheat, but the main reason I'm showing you this is that adjustment stem on the bottom. Again, you might not see this very often. Take off the cap, make your adjustments. But let's just say you're being put through the ringer. You've checked your filter, you've cleaned the coil outside, you've done your subcooling, and just things, the math ain't mathing. Things don't seem right, and you suspect that somebody before you, I mean, we've all gone behind bad techs before, and you're just scratching your head like, what is going on? They way overcharged it or something. If you think they were just cranking on that thing and you last ditch effort, you at least would like to factory restart those settings. So you were going to turn it counterclockwise, you're going to turn the unit off, turn it all the way counter until you feel that spring like bottom out. You will then look at your manufacturer, your family, your refrigerant, and your temperature, and it'll tell you the number of turns. That you can do fast. The system's not running. You're not worried about it reacting because it's not on right now. Go ahead.
Turns like 360 degrees around?
Yes,
For one turn?
one
Okay.
full turn, 2 full turns, 3, 4. That's going to give you a starting point. So now, turn your system on. Be patient. Remember, TXVs take time. Even with an orifice, you should take your time. Give it 5-10 minutes. Let it do what it's going to do. Let it balance out. Take your reading, and then adjust it. Now, you're going to adjust it slow. Quarter turn, half turn. If you feel like it's way off, half turn, I heard some guys that smoke joke around saying, that's your 3 cigarette break right there, because you're gonna adjust it 1 cigarette, adjust it 2 cigarettes. Obviously, I don't agree with that, because if you're a smoker, you shouldn't be smoking outside a customer's house. That's just me. So, again, the only time I'd like to see you do that, I've only messed with one ever. And again, that was like the last ditch effort. I'm just trying to see how much superheat I can get out of it. You won't see that very often, and most of them don't even come with that adjustment. So, to recap, the purpose of a TXV, it's a metering device. It's going to help keep all the refrigerant in that evaporator as possible without overheating it. It's also going to protect your compressor. That is the main concept there. We do not want liquid going to your compressor. If you're ever charging it and you hear that compressor start to growl a little bit, calm down. Maybe remove a little refrigerant, but I usually only have my gauges going up maybe 10 or 15 PSI at a time. Don't just crank that in there. You're gonna flood that compressor, and that is not good. And again, it responds to temperature and pressure only. It takes the temperature of the line, it builds up pressure in your bulb, which in turn puts pressure your opening force. Then you have the pressure from your spring, and you have the pressure coming in from your equalizing line, which is your evaporator pressure. Does not control, because people think this. They think this just controls everything. It is not what controls things. Space temp, again, it reacts to space temp. It does not control it. That is controlled with a thermostat. Head pressure, where do we control head pressure at? Anybody remember? Condenser, absolutely. And there's ways to control. We won't, again, without going into like a basic refrigeration class. A fan cycling device is what you guys will probably see the most. Has anybody installed one? A fan cycle switch? I mean, they make like Renko with all these adjustments, or they just make one you can just key in, and that's what you'll see most. I mean, sometimes you just gotta do that for rooms that need to run year-round, obviously. So, server room, it's going to need AC year-round. If it doesn't have a mini split, something that's going to monitor all that for you, it's just going to control your head pressure by turning the fan on, off, on, off. Capacity. You guys are service techs. I don't know if any of you do evaluate a house first and size it appropriately. I don't know if that's your sales guy, but capacity, super important. You do not want to oversize a house. What happens if you oversize cooling in a house? It's like you think, if it needs a 2.5 ton, but I'm gonna put a 3.5 ton because I think that's gonna work so much better. What's gonna happen?
You won't get enough airflow.
Humidity. It's gonna cool the house so fast that it didn't have time to remove the humidity. Now your house is gonna feel gross. It's just not gonna feel like a conditioned space. And that's why we call it air conditioning. We want the humidity to be a certain level to be comfortable. So Same thing with rooftop units. I mean, I've seen them where they've oversized them. I might just take second stage out of it. Get longer run times and then it'll get there. Once it removes that humidity, that temperature will drop. I've always told my customers that, you walk in, it hasn't been working, it has a bad capacitor. Now it's 85 degrees in their house. You go to leave, you turn it on, they're going like this. Well, that's not very cold. Well, of course it's not. It hasn't removed the humidity yet, and what do you get across your evaporator if you're taking temp drop? What do we want to see? 18 to 20. 85 degrees minus 20 is what? 65, right? So now you're going, that isn't that cold, because normally you're at 70. 70 minus 20 is 50. You're used to going, wow, my AC is working great, it's 50 degrees, that's cold. So you gotta tell the customer, like, listen, this is gonna take probably 4 hours if it's 85 degrees and hot out. Close your windows. Give it time to remove that humidity. I promise you, when it removes that humidity to a certain percent, that temp will start to drop. Suction pressure. Since we're going over a review, what controls suction pressure? That is your it is your airflow. So the suction pressure, head pressure is outside. That is your condenser. Suction pressure is inside. Picture it like that. That's how I always kind of try to think about it. Your airflow. If your airflow is going very slow, clogged coil, dirty fan blades, and now your airflow is slowed down, but your system's designed to be a certain way, that evaporator is going to get flooded, and then it's going to start to ice up. I'm sure you guys have seen that, and you're like, you see why it's a dirty filter. But that is why the fan speed is probably the most important thing in AC. If you can take a airflow class here, there's a guy downstairs named Mark Ham. He's been doing this 50 years, probably the smartest man I've ever met in my life. I'm glad he's not here to hear that. But learn about airflow. I promise it'll change your life. They didn't stress it a lot in my job. I kind of learned it over the years, just picking it up. But if you're not taking your airflow differences, you can't just trust your installer to have everything dialed in, especially nowadays. Everything's modulating, there's settings. It's a little more complicated now. So suction pressure, although it does react and help maintain suction pressure, it does not control it. Humidity, what controls humidity? Anybody remember? It's your evaporator. Again, the can of pop. You have warm air, saturated air blowing across your coil, and it's cold, so it starts that humidity starts catching on there and changing state into droplets, and then it drips down there. That's how we're removing humidity out of the house. Before we get into troubleshooting, we can take a 15-minute break. Again, bathrooms down the hall. If you need to smoke, go all the way to that door, downstairs and out that door. If you guys want to see the